Good evening, President, Vice Presidents, past Presidents, members, ladies and gentlemen. It's my honour as Director General to welcome you here this evening to the Presidential Address for 2025. It's a great pleasure to see so many attending in person, and I'd also like to extend a warm welcome to the wider engineering community who are joining us online this evening. You're very welcome. Before we start, I have three short housekeeping points. We're not planning a fire drill this evening, so if the fire alarm sounds, please exit via the door to your right, behind me, and through the doorway you entered, if safe to do so. Please switch off your mobile phones. And thirdly, for those who are tuning in virtually, there will be an opportunity to ask questions after President John Jordan's address. Therefore, if you'd like to pose the questions, please email president@engineersireland.ie. That's president@engineersireland.ie. Those of you who have joined us in person are also encouraged to get involved by raising a hand during the question and answer session. And now to our Presidential Address. The Presidential Address is the highlight of the Engineers Ireland calendar. Looking at addresses of past years, we can see and appreciate the knowledge and wisdom imparted by previous holders of the office of President of Engineers Ireland. John Jordan is Managing Director of Wirtgen Ireland Limited, a sales and service subsidiary of the German premium equipment manufacturer specialising in road construction equipment and plant for the mining and processing of minerals. John's early career was spent with Roadstone, where he held several roles before joining SIAC as Business Development Manager. In 2007, John took up the role of Managing Director of Wirtgen, where he leads the company's overall business in Ireland. John has served as Chair of the Finance Committee at Engineers Ireland, now the Finance Audit and Risk Committee, since 2018, playing an active role on Engineers Ireland Council and Executive Boards during his tenure. He has also served as member of the Audit and Risk Committee, the Benevolent Fund Committee, Engineers Club Committee, and is outgoing Chair of the CPD Standing Committee. John is also a member of the Midland Region Committee and was previously Chair of the region in 2011 and again in 2018. John is a graduate civil engineer from University of Ulster. He holds an MSc in Technology Management from University College Dublin and is a Chartered Engineer and Fellow of Engineers Ireland. In addition, he holds an ACCA Certified Diploma in Accounting and Finance, an MIQ in Quarry Management, and a Diploma in Company Direction awarded by the Institute of Directors. John was inaugurated as Vice President of Engineers Ireland in June 2023 and as President of Engineers Ireland in May 2025. Would you please welcome President John Jordan to the stage, please.
Thanks, Damien. Thanks, everybody, for joining us tonight and everybody for joining online. Very welcome. As technology takes on a greater role in our workplace and personal lives, it can feel like we are living through a science fiction novel. But however surreal it feels, there is no question of our technological progress rolling back, halting, or even slowing. As the novelist Isaac Asimov said, it's engineering that changes the world, but can we be certain it's changing it in the right ways, or that engineers have the tools or frameworks to determine right from wrong? Move fast and break things was a mantra. A lack of respect for tradition or accepted norms is crucial for innovation, but safety is often the greatest victim of speed. Polling conducted for Engineers Ireland consistently shows engineers to be one of Ireland's most trusted professionals. But this evening I would like us all to consider whether we need to do more to retain and build that trust. My address this evening asks, what are the ethics in engineering and what do emergent technologies and new problems and new global problems do to challenge our notions of right and wrong in our profession? Let's start with something ordinary, an ordinary day. A kettle clicks on in a quiet kitchen. A phone lights up on the counter and shows a small blue dot on a map. A bus rolls past the window. A bridge in the distance carries cars from one town to the next. None of this feels dramatic. It's everyday life. Yet, every one of those moments carries engineering choices behind it. The phone map depends on satellites and networks planned decades ago. The bus and the bridge depend on people who thought about loads, rain, wind and wear. And the kettle depends on metal that can heat and cool thousands of times and still function. Engineering is like that. It hides in plain sight. It turns ideas into things. It turns plans into routes and roads. It creates devices that help us live the lives we want. This talk is a story about engineering and power. It's a story about the importance of ethics and proper professional conduct, how we've used skill and knowledge to move people and change places. It's also a story about purpose. A bridge and a battering ram both use maths and materials. One opens a path, the other breaks a door. The difference is the reason that we built it. So here's the simple question that follows us the whole way through. When we build, who and what do we empower? I will start with a set of short scenes, simple scenes on purpose. One place, one choice, one lesson. We'll walk from the past to the present, and then we'll end up with a set of promises that can be carried back to guide any team, any workshop, any whiteboard. Next slide. Long ago, a pale strip of stone ran across a warm plain. The surface was made slightly curved so rain ran off. Underneath were layers that made it strong. To the eye, the road looked straight for miles. People often imagine families and carts moving along it. That happened, but it came later. Those famous roads were built first to move legions bent on conquest. Straight lines meant speed and planning. A crown surface shed water and lasted longer. A layered base carried heavy loads without sinking. These choices turned a plan into a promise. The commander could say, "We will be there in 5 days," and be right. Trade and culture came after, but the first use was the army. Design intent becomes public fact. The reason for a design lives on in the design. In the eastern Mediterranean, there are tall wooden frames in the sand. Ropes hang from pulleys. Bronze fittings shine. Craftspeople tie, measure and test. They're building a moving fortress. People later call these machines the Helopolis, the taker of cities. A tall tower on wheels, faced with plates on the side that would meet arrows and fire. Inside are catapults that can throw stones and bolts. The tower doesn't rush, it moves slowly towards the city wall, heavy and steady like a building that learned to walk. It's a marvel of planning and teamwork. It's also a very clear message. Geometry, wood, metal and rope can become pressure against a wall. Knowledge can become force. The lesson isn't that such things should never be built. The lesson is that engineering answers the questions it's asked. If the question is, how do we break a wall? We might find a brilliant way to break a wall. The grasslands of the Mongolian steppe. A rider draws a small bow while moving at speed. The bow isn't a simple stick, it's a composite. Layers of wood, horn and sinew, glued and wrapped together so that the material shares the strain. The wood bends, the horn resists compression, and the sinew resists stretch. Together they hold more energy than any one of them could alone, and the arrow flies far and fast. The bow was part of a larger system. These Mongol riders moved quickly. They had scouts and supplies. They rotated horses to keep speed. They borrowed what they needed. And if they met a good idea, they took it. If they found a skilled builder or a siege expert, they brought that person along. The system was not one tool, it was many tools that worked together. Technology plus method plus logistics beats technology alone. A great tool without a great system is just a tool. A good system turns a tool into a force. Gunpowder changed everything about walls. Tall stone walls had once felt safe. Now cannon tore holes in them. Engineers did not simply build higher. That would have been easy to hit. Instead, they changed the shape of defence. From above, new forts looked like stars. Low, thick faces met cannon fire at angles, so the shot struck glancing blows. The spaces between the points allowed defenders to fire along the wall, which is the worst angle for anyone trying to climb it. Ditches, slopes, and paths were laid out like clockwork. In France, a planner named Vauban turned this into a full system of defence. Inside the walls, streets, doors, and water were arranged for long sieges. The town and the fort became one machine. The lesson is that engineering can redraw maps. New weapons force new shapes, and new shapes change how people live. Iron rails and copper wires did something new. They changed time itself. A trip that took weeks now took days. A message that took days now took minutes. When one country could move soldiers by train and another could not, the result on the battlefield was not even close. Later in World War I, trains were not just helpful, they were part of the weapon. They moved shells, food, and people into a machine that could not be fed. Engineering speeds up decisions. It makes new plans possible and old mistakes bigger. Speed does not guarantee wisdom. It only multiplies what is already there. Chemistry made fertilizer by pulling nitrogen from the air. This was the Haber-Bosch process, which produced ammonia and nitrogen fertilizers that significantly increased crop yields. Populations grew because food became more plentiful. It's one of the great gifts of science. But the same chemistry also made explosives easier to produce. And this same chemist who worked on fertilizers helped turn chlorine gas into a weapon in World War I. In one life's work, there was life and death. The same skill can serve more than one result. This isn't new. It's the reason we should ask not only, can we do this, but also, why would we? And what else follows from this? At Bletchley Park during World War II, a team of people tried to read what the enemy had hidden. They were a mix of linguists, mathematicians, engineers, and organisers. At sea and in the air, knowledge can decide lives. The enemy used a cipher device called the Enigma machine to scramble messages. Those messages were orders, locations, and plans. The work at Bletchley was to turn scrambled text back into meaning fast enough to save ships and win fights. To do that, the team designed and built electromechanical machines called bombs that swept through many possible settings in hours. Later, they built Colossus, a large electronic machine that used valves to do logical steps faster than any team of people could. The result is both practical and historic. The war was likely made shorter because of the work at Bletchley Park, and modern computing took a large step forward as a result of the advances made. You can see a line from those huts at Bletchley Park to the laptop in your bag and the phone in your pocket. A need drove a tool into being. That tool had children and grandchildren we now use every day. Meanwhile, across the Atlantic, a network of labs and plants worked on something that had never been done before. The Manhattan Project brought physics, chemistry, metals, explosives, and timing together. The job was to make a device that unleashes the energy in the nucleus of an atom in a tiny moment. When the first test happened in a western desert, people saw a light like a second sunrise, and it felt a heat like an oven door opening in their face. It was a line crossed. The war ended soon after. Some felt pride, some felt grief. Many felt both. One scientist, Joseph Rotblat, had already left the project when he believed that the purpose had changed. He spent the rest of his life working to limit nuclear danger. Technical success can leave a moral echo. The job can be done and still leave questions behind. That doesn't mean the job should never be done. Sometimes the hardest part is deciding whether to proceed, when to pause, and how to speak when a project's purpose shifts. It's easy to think of military and civilian technology as separate shelves in a library. In reality, many of our daily tools began life on the other shelf. GPS was built so that planes, ships, missiles could know where they were with precision. Now it's in tractors that steer straight roads, in ambulances that find the fastest way to a patient, and in every phone that helps you meet a friend. The ARPANET, a research network funded for national defence reasons, has become the internet that we use every day. This crossing of purpose brings gifts and new duties. It shows that tools made for defence can become tools for everyday life. It also shows that our common world often depends on designs made for very different aims. This should make us very careful. It should make us ask early and often, what will this invite years from now, and for whom? We are teaching machines to see better, predict better, and act faster. In many places, this is good. Cars can hold a lane, lights dim and brighten to save power. But when a tool can harm, speed is not only a gift. If a machine can choose a target and act in the blink of an eye, who's the one responsible? A long-standing voice in war and law, the International Committee of the Red Cross, has said 3 simple things. Keep real human control over decisions to harm. Do not build systems that are unpredictable and can harm. Do not build systems meant to harm without a person deciding. These rules remind us, systems do not stand alone. People design them, deploy them, and answer for them. We're now building tools that learn from patterns and make predictions and even create. These tools are not just faster calculators. They are systems that can write, draw, speak, and decide. They help doctors read scans. They help farmers track crops. They help coders find bugs. They're already part of daily life. But scale changes things. A person can lie to one friend. A machine can lie to 1,000,000. A person can make a mistake in a spreadsheet. A machine can make the same mistake in every school, every court, or every clinic. When we give a system the power to act at scale, we must also give it the duty to act with care and keep people in the loop. In some places, AI helps people do better work. In others, it replaces people. This is not always right, but it's not always wrong. A tool that helps a nurse is not the same as a tool that replaces one. A tool that helps a judge is not the same as one that gives a sentence. We must ask, what is the role of the person and what is the role of the machine? When a system can act, we must ask who is in charge, not just in name but in fact. If a system causes harm, who answers? If a system is used to deceive, who's responsible? These are not only technical questions. They are questions of law, of ethics, of power, and of people. AI is not one thing, it's many things. It's a tool, it's a partner, it's a mirror, and a force. It can help us to see more clearly, or it can blur the truth. It can help us to work faster, or it can rush past what matters. It can help solve hard problems, or create new ones. Think about an AI system that predicts equipment failures in a power grid. Done well, it prevents blackouts and saves lives. Done poorly, it can trigger unnecessary shutdowns or miss a critical fault, and millions sit in the dark. The same technology, the same code base, 2 very different outcomes. There's another change that touches us all. Software can now make a video and audio that looks and sounds like real people. A clip can appear of a leader saying something they never said. The face looks right, the voice sounds right. If a clip like that lands at the wrong moment, it can move people in the markets before anyone checks it. The answer is not to stop believing what we see and hear. The answer is to make the truth easier to check. Truth should be harder to fake and faster to confirm, because people and lives may depend on it. More education is required around this technology and its risks, especially for people over 20. As technology moves at an exponential rate, so must society's reaction and response. Engineers are not just builders. We are the translators of values into code. Every line that we write, every model that we train, every shortcut we take, these are choices. They shape what the system can do and what it might do. They shape who benefits and who bears the risk. Consider a self-driving car. If its sensors fail to detect a child crossing the street at night, that's not just a technical glitch, it's a design decision about what data mattered, what edge cases were tested, and what trade-offs were made. Lives can hinge on these choices. Ethics is not a final check, it's a first principle. It starts with the questions that we ask, the data that we use, and the defaults we set. It continues in how we test, how we monitor, and how we respond when things go wrong. It lives in the meetings we hold and the metrics we track and the incentives that we reward. When a team decides to optimize for speed over safety or engagement over truth, that's not neutral, it's a choice that shapes the world the system creates. We must resist the idea that the system decided. No system builds itself, no model trains itself, no deployment is neutral. If a tool can be used to deceive, to exclude, to harm, then we have to ask, what would it take to prevent that? What would it take to notice it early? What would it take to stop it? Personal responsibility matters. Reports from war zones show that now small drones are dropping explosives on civilians and striking ambulances near front lines. Cheap hardware plus easy software makes targeting simple and the distance safe for the attacker. This is what happens when consumer technology becomes a weapon with a software update. We can't say we never imagined it. We must imagine it and design accordingly. Something else travels through fibre and air. It has no weight and no smell. It's code. And when code becomes a weapon, the damage can spread silently and fast. Think of a worm, a self-replicating program that moves from one system to another without asking. One clever worm can slip into a hospital network, shut down lights in an operating room, or corrupt water treatment controls. It doesn't need bombs to harm people, it just needs access. The rules of humanitarian law do not vanish because a weapon is digital. Distinction, proportionality, and precautions still apply. The law expects restraint, and our systems should too. Simple idea: in critical systems, we build for containment, predictability, and safe failure, because people depend on them. "3D printers are changing how we build. They can generate complex metal or plastic parts layer by layer, cutting costs and speeding development. NASA has flown 3D printed rocket engine parts into space. Car makers use them to produce lighter components in days instead of months. This is real progress. But the same printers can also make firearms or components that turn a harmless tool into a weapon. A file downloaded from the internet can become a gun in hours. When tools turn files into force, we share responsibility for how easily that force can be misused. The answer is not locking every workshop. It's building smart checks into the process. Software that flags restricted designs and printers that require a license for high power modes. Because when a printer can make a rocket or a gun, the question is not just what it can do. It's what we design it to allow and what we design it to prevent. Two families of tools now sit on the edge of speed. One is hypersonic systems, vehicles and missiles that move many times faster than sound and can change course mid-flight. The other is directed energy weapons, devices that use beams of light or waves to disable targets in the air. Both promise new abilities, both demand careful rules. Hypersonic missiles can cross continents in minutes, shrinking the time leaders have to think from hours to seconds. Directed energy weapons can stop drones without firing a shot, but if used carelessly, they can blind satellites or disrupt civilian systems. We've already come close many times. The ethical challenge is simple. Speed changes responsibility. When decisions happen in seconds, how do we keep human judgment in the loop? And when energy weapons can disable without warning, how do we protect civilians and critical infrastructure? These choices cannot be left to machines. They belong to people. Building fast is not the same as building blind. Speed without judgment is risk. Systems need speed, but they also need restraint. And restraint is human. DNA editing is no longer science fiction, it's here. CRISPR is already being used to treat genetic diseases. In fact, the first FDA-approved CRISPR therapy for sickle cell disease is available today, and personalised treatments have saved lives for rare disorders. In agriculture, CRISPR is helping create crops that survive heat and drought, protecting food supplies as the climate changes. This is powerful and risky. The same tools that cure disease could, in the wrong hands, create a virus that spreads faster than we can respond, or a crop that disrupts ecosystems. When the ability to rewrite life becomes widely available, the question is not just what we can do, it's what we should do and who decides. Ethics is not paperwork, it's design. It lives in the defaults we set, the oversight we build, and the transparency we demand. It means asking at every stage, why is this safe enough to continue? And what would change that answer? It means systems that invite scrutiny, not secrecy, and incentives that reward caution as much as speed. Because when you can edit life, the stakes are not just theoretical, they are human, and trust must be engineered in from the start. The world urgently needs steady, clean energy. Small modular nuclear plants built from factory-made pieces could change the game. They could power remote towns, heat factories, and cut carbon at scale. Rolls-Royce is already developing designs for the UK, and similar projects are underway in Canada and the US. Imagine a plant the size of a football field delivering energy for hundreds of thousands of homes without the emissions of coal or gas. But every promise carries a shadow, and these plants raise questions that cannot wait. How easy are they to inspect? How do they shut down safely? How do we manage fuel and waste for decades? The answer is smart design, clear inspection rules, transparent reporting, and fail-safe systems built in from the start. Because when nuclear power goes wrong, it doesn't fail quietly. The upside is huge: clean energy, reliable supply, and lower carbon for generations. The risk is real. The future depends on whether we design for both. Of course, fusion could be a game changer here. We've travelled from stone roads to digital code, from siege towers to satellites, from cannons to lasers. But most of the real work doesn't happen in epic battlefields or grand speeches. It happens in ordinary rooms. A desk with a laptop, a whiteboard with arrows, a team on a video call, a quiet moment before a decision. Ethics isn't something that shows up at the end in a legal review. It starts with the first sketch and the first line of code, the first what if scribbled on a sticky note. It lives in the habits and questions, quite practical and persistent. We end where we began. A kettle clicks off, a phone lights up, a bus rolls by, a bridge carries cars. These quiet, ordinary moments are powered by decisions made in rooms we'll never see, by people we'll never meet, engineers, designers and planners. People who made choices that shaped the world, often without applause, often without knowing whose lives they touched. This is the quiet truth of our work. What we build becomes the world others live in. Ethics doesn't need a podium. It doesn't wait for a crisis. It lives in the early questions, the small hesitations, the moments when we choose to do it right instead of just getting it done. It's not a grand gesture, it's daily practice. We carry 5 promises, not as rules but as reminders, not as burdens but as guides. We hold people safe. We don't trade safety for speed. We don't gamble with lives we'll never see. We look for misuse before someone else does. We imagine the ordinary ways things can go wrong, and we build to catch them. We keep a human at the point of harm. No system should make moral decisions alone. We build with the law, not around it. Rules are not obstacles. They are the voice of the public in our work. We speak up. When something crosses a line, we don't stay silent. We act. These are not just professional standards, they are personal commitments. They are the difference between building something that works and building something that matters. Because engineering is power and ethics is how we aim it. We won't always control where our work ends up. We can't always choose who uses it or how, but we can choose how we build it. We can choose what questions to ask, what risks to name, and what lines not to cross. In the end, the most powerful tool in any room isn't the code or the circuit, it's the conscience of the person holding the pen, writing the spec, or pushing the deploy button. Thank you very much. I'll just move it back to the first slide.
Thank you, President, for that insightful presentation on what is the true essence of a professional engineer. I would now like to call on our Vice President, Dave Murphy, to propose the vote of thanks. Dave, you're welcome to the podium.
Thank you, Damien. And firstly, thank you, John, for and well done for what was a very, I think for all of us, a very thought-provoking and probably a very timely subject that you picked for your address tonight. I guess in terms of challenging us all as engineers, particularly I guess at this time when technology is changing so quickly, and you rightly pointed out that we see it in our everyday lives. Anybody listening to the radio today would have heard the discussion, I'm sure, multiple times about how soon autonomous taxis are likely to be here in Ireland. I'm sure many of you here in the room are dialed in on the Zoom call tonight have already travelled in autonomous taxis in the United States. Looks like they're coming very quickly to Europe. You give several really interesting examples of how a technology that probably originally was designed for good, the same drone that can deliver your Thai takeaway, could also deliver drugs to your door, could deliver weapons, could drop a bomb. So, you know, what you said at the end there, you know, the challenge, and it is a huge challenge, that when, you know, we design and we build complex equipment, our processes, our buildings, that we've got to think about how could, you know, firstly, obviously it has to be designed, you know, as best we can to be completely safe for those who use it, those who occupy it, you know, long into the future, those who maintain it, the people that are building it. but then to also think about, well, how could this either deliberately or inadvertently be misused? That very same system, that very same process, that very same technology. And that's not easy. But I think it's right that you raise that question tonight, and you challenged us and you outlined some very good principles there at the end, or the promises that we make to ourselves as engineers. And obviously, we're not perfect, and we can aspire to be as close to perfect as we can. But in the end of the day, usually we operate with checks and balances. We operate in teams and with groups, and that, there's no single point of failure. One person isn't left completely responsible for a system or process. There has to be a check. Somebody's got to review it, somebody's got to check it, somebody more experienced, somebody independent, but also that we don't allow a technology to check itself. I mean, I think we'd all agree that that is not somewhere that we want to go, that there's got to be a human along the line that's reviewing and checking it, and hopefully we never get to the point where technology, artificial intelligence is making decisions for all of us with no human intervention, no human checking. So again, well done again tonight, John, for raising that topic, particularly at the juncture that we're at with artificial intelligence. I think it probably excites us at one level. I'm sure everybody here is using ChatGPT and whatever, but it also frightens us. And particularly in the engineering profession, it's got fantastic potential, but it also has worrying, I suppose, for all of us. And we always have to worry as engineers. That's probably why many of us have no hair, like myself. We're worriers because of the huge responsibility. And it is a serious point. Engineers carry a huge level of responsibility. Everything you see around you, everything we use, the buildings we live in, the infrastructure we use, the systems used, the phone in your hand, it all involves engineers. So it's a huge responsibility, but we've got to be constantly, I guess, vigilant to make sure that those systems, those processes that we design and build are safe and are not open to use. So well done again, John. And I now propose that the best thanks of Engineers Ireland be extended to President John for his address, and I request his permission to have the address recorded in the transactions.
Thank you very much, Dave.
And I would now like to call on Vice President Una Parsons to second the vote of thanks.
Congratulations, John, and thank you for taking us on such a compelling journey through the history and future of engineering. You didn't just tell us a story, you gave us a powerful reminder that engineering is inseparable from ethics. Your statement, ethics is not a final check, it is a first principle, captured the essence of your message. Through a narrative that spanned from ancient roads built for armies to siege technologies and onto today's AI-driven decisions, you showed us that the ethical dimension of engineering has always been present and is now more important than ever. You left us with 5 powerful promises, principles to guide each of us as engineers. We hold people safe, we look for misuse before someone else does, we keep a human at the point of harm, we build with the law, not around it, and we speak up. And then you closed with a message that couldn't be more timely or more true. Engineering is power, and ethics is how we aim it. I have pleasure in seconding the vote of thanks for an excellent and most interesting address, and I ask you to join me in expressing your appreciation to the President. Thank you, John.